9 common parasites that invade our koi. Occasionally, we also detect parasites that are not so common. This video, however, will concentrate on the 9 you are most likely to find. When identifying parasites, an essential part of your armoury should include a microscope for positive identification. Microscopes come in different shapes and sizes, sporting various gadgets and filters. Depending on how much you are willing to pay, there are monocular with a single eyepiece or binocular with a double eyepiece. The binocular type tends to be much more expensive. If you can afford it, you could purchase a camera that sits on top of the microscope. You can then view your specimen much easier on a television monitor. In addition, you could add a video recorder and tape your results for future reference, adding later results to the same tape. You could eventually assemble your very own parasite collection. Although some parasites can be seen by the naked eye, much more detail is noted after magnification. Even under the microscope, identification can be quite daunting for the novice. Therefore, as much practice as possible with your microscope is of paramount importance, and to familiarize yourself with using different focal lengths, making good use of your object lenses. Also, you need to find the correct way to systematically view your slide. The best method is to first search the periphery of the sample. Parasites can be more readily observed in the clear fluid area, especially smaller parasites like Costia. Next, proceed by scanning from side to side, moving down 1 pitch at a time so you cover the whole slide. This process can take quite a while to complete correctly. You will need a slide and cover slip. You will also need an instrument to take the scrape, although most people use the slide itself. If you decide to use the latter, care must be taken, or damage to the fish's skin or scales could be the result. Fish are susceptible to muscle spasms when the scrape is being taken. For the expert, it is rarely a problem, but for the novice, possibly the safest way is to slightly sedate the fish to calm it down. The scrape can then be safely carried out. With the fish under sedation, a quick inspection of the gills would be appropriate, as it is good practice to inspect the gill condition whilst you have the opportunity. Maybe the problem is a gill condition, causing the fish to show signs of irritation in the first place, prompting you to take the scrape. Catching a fish is a simple operation if it is done in the correct way. First and foremost, make sure you have the proper equipment to do the job. Your net should be of an adequate size, and the transfer to the bowl should be a smooth maneuver. Using a koi sock for this purpose makes the job much easier, and the fish can be transferred safely. If a koi sock is not available, another option is to put the fish straight into the bowl. Lower the bowl into the water sideways, with its rim within the net perimeter, and partially fill as the transfer takes place. Anesthetizing the fish is quite a simple operation for the experienced keeper, but can be a little daunting for the novice. The legally recognized fish anesthetic is MS-222, which can be purchased from a veterinarian or at any pharmacy. There are various substances some people use that are not legally recognized for fish use. However, for safety reasons, if you must use something else, what we will say is that you must follow the manufacturer's instructions to the letter on usage and dosage rates. As mentioned before, it is a good opportunity, whilst the fish is under sedation, to carry out a gill inspection and possibly have a quick look for any other damage. If for any other reason you need to keep a fish out of water for a longer period, you need to give it a test lift. Raise the fish out of water, spacing your hands underneath it to evenly take the weight. Hold it in that position for about 10 seconds. If it flips, replace it in the sedative and try again after a while longer. Once the fish remains quite still, you can then proceed. Always remember to wear rubber gloves when handling fish, making sure that they are wet. This procedure is as much for your safety as the fish, as some fish diseases can be passed on to humans. After taking the scrape, bring the mucus to the center of the slide, place the cover slip over the specimen, and in a hinge movement, lower gently to ensure no air bubbles remain. Gently apply pressure to the slip with your finger to slightly compress the sample and place your slide under the microscope. As we said earlier, it is always advisable to completely view the periphery of your specimen first, as parasites can be seen easier in the area of clear fluid surrounding the mucus. Identification of juvenile stages is especially hard for the beginner, as they can be quite different to those you see portrayed in books. Good examples of this occur when viewing different life cycle stages of white spot and anchorworm, due to them passing through multiple changes. Just for easier identification purposes during this video, we will refer to parasites using their common names as most koi keepers know them by. Basically, we will list the 9 parasites that we intend to cover in depth. White spot, skin or body fluke, gill fluke, fish louse, anchorworm, leech, Trichodina, Chilodonella, and Costia. White spot is a parasite that evolves through its life cycle, adopting many different forms, both morphological and physiological. All these changes take place in the water, either on the fish or on any resting place in the pond. They can also form a latent stage if reproduction requirements are not conducive. This is the reason that white spot will disappear after treatment and then mysteriously reappear when new trigger factors are introduced. This is achieved by some cells going through a sexual process, fusing together with a cell of the opposite sex. This creates a new cell in the form of a cyst, hence their magical reappearance. During their latent stage, they cannot be affected by chemicals. Most white spot, viewed under a microscope, will not show the typical horseshoe shape usually illustrated in books, as it is usually juveniles you see first. In this rare view, you can actually see the white outline of the horseshoe. A magnification of 200 times is best for identification, especially when viewing juvenile stages. All plants and equipment are capable of transmitting white spot. Adult stages will leave the fish and begin to multiply within their nucleus. When the parasite is fully ripened, it eventually bursts, releasing thousands of young tomites, sometimes referred to as swarmers, into the water, all eager to find a new host. This view shows one such organism in the process of bursting as it rapidly changes shape. Once released, they efficiently move through the water using a ring of fine cilia, which they beat profusely, and which under the microscope appear as a fine blur as seen in this view. If temperatures are favourable, this change can take place in about 20 hours. Once a swarmer finds a host, the whole life cycle starts again. It is easy to understand how a fish can soon become debilitated with such speed of reproduction, and will definitely end in multiple fish mortalities. Therefore, it is essential to deal with this parasite as soon as it is identified. If young swarmers fail to find a host within about 24 hours, they will die. Moving on to skin fluke, sometimes referred to as body fluke. This parasite is easily identified by certain characteristics using a magnification of 1 to 200 times. This would be adequate for positive identification. Different to other parasites, skin flukes give birth to live young. If given the choice, it would also like to spend its entire life on the host. There is a very good reason for this, as it is very immobile in water, and the only way it can successfully board a host is by direct contact. They move around their host by using suckers on both ends of their body, which excrete a gluey substance. On their anterior end, there are 2 central hooks surrounded by a ring of 16 smaller hooks. Embryos of future generations can sometimes be seen inside the adult. They are continually giving birth in conveyor belt fashion and can produce many thousands of young within a month if conditions allow. Under normal conditions, healthy fish produce antibodies which are contained within their mucus. This action helps to keep the parasites under control. Only when fish become debilitated in some way will they submit to parasite infestation. At this stage, human intervention is required. Skin damaged by the vicious use of their hooks will invariably make way for secondary bacterial and fungal infections. This action can clearly be witnessed on this video. Here we see the gill fluke. Differing from the skin fluke, the gill fluke is an egg layer. They are also only a quarter of the size of skin fluke. Therefore, 200 times magnification would be more appropriate. They are easily identified by 4 black eye spots on their anterior end, as can be seen here. They prefer to stay in the gills, but can sometimes be found on the body. At the posterior end, they have hooks for anchor purposes. The efficiency of the eyes is not as we know it to be. They perceive the fish as a shadow, and this becomes their target. The gill fluke life cycle passes through 3 stages, these being larva, juvenile, and adult. Most of their life is spent on the host. They attain sexual maturity in 3 to 6 days. In 4 to 5 days, larvae will develop into adults. When fish are half grown, they develop a certain resistance to gill fluke, and providing fish are healthy, they will keep the parasite under control. The gill fluke is hermaphroditic and not needing a mate of the opposite sex to reproduce, so this ensures a much faster reproduction rate. The fish louse is a crustacean parasite and is therefore in possession of a tough exoskeleton, which vastly improves its protection from external sources. It attaches itself to the host by using 2 sucker-like organs and its 2 antennae with clasping hooks. It pierces the fish's skin and feeds on blood by using its stylet mouthpart. It also injects an anticoagulant into the damaged area to ensure a free flow of blood. They are not host dependent entirely and can survive for long periods away from the host. Fish lice can hibernate embedded in the host body during lower temperatures and progress the life cycle when temperatures increase. No known chemicals are effective against the parasite in the egg stage. However, all stages are sensitive to drying out. From the second copepodid stage, the parasite develops paired swimming legs on all 4 thoracic segments which enable it to efficiently move within the body of water it inhabits. Amphibians and plant life may also assist in the transmission process of the parasite. It is also possible for the parasite to be moved short distances on the plumage of birds. As the common name suggests, female anchorworm have the ability to penetrate the fish skin and firmly anchor themselves, burying their heads deeply into muscle tissue and various organs including the gills. The head continues to develop into a twin structure using a process called the cephalic process, and this can clearly be seen here. During the cephalic process, anchors or hooks develop which assist in holding the organism in place during the remainder of its life. The male anchorworm dies after fertilizing the female and plays no further part in reproduction. Therefore, the male is no real direct threat to the host. Having achieved this stage of the life cycle, the female will not respond to chemical treatment and is fully protected. The only course of treatment at this stage is manual removal with the fish sedated. All other life stages are sensitive to treatment. After various life cycle changes, using a molting procedure, the parasite attains a copepodid stage where two pairs of swimming legs develop. At this stage, the parasite must find a host within about 3 days or it will die. Anchorworm can be seen more easily when the fish is in water. They have the appearance of a white piece of cotton anchored to the fish's body, wavering in the direction of the water flow. Once the fish is removed from the water, the parasite clings firmly to the body of the fish and can seem quite invisible. The leech is not entirely host dependent on a continual basis. It can survive for many weeks away from the host after a satisfying feed. Leech are hermaphroditic, therefore do not need a particular mate for reproduction. Similar to the fish louse, it injects an anticoagulant into the host to ensure clotting of the blood does not occur. Its main strategy for survival is ensured by laying its eggs in a protective cocoon, which is resistant to all known chemicals that can safely be used for fish. Having said that, all other stages of the life cycle are sensitive to treatment. All stages, including the cocoon stage, are sensitive to drying out. In lower temperatures, they can survive for months in the cocoon stage, which makes it very difficult to eradicate. Therefore, it is difficult to know when a hatching is taking place, as this would be the appropriate time to introduce a treatment. They are highly mobile in the water, and they can get their food supply from many sources, including most aquatic inhabitants and the waterbird families. They are very efficient swimmers, as they wriggle their long, slender bodies in a snake-like fashion. The unsuspecting passing fish has no chance of escaping their ability to attach and detach at will. This practice can clearly be seen here, as the leech makes a beeline for its intended victim. Did you miss it? Here it is again. And again. Now you can see it firmly attached. Trichodina is very mobile and does not necessarily need a host to survive. It feeds mainly on bacteria and therefore, once again, is not host dependent. It uses its host mainly for transportation purposes. Consequently, it is not classed as a real parasite. Our usual view through the microscope gives us the impression that it is a flat disc. However, viewed from a different angle as seen here, clearly shows its true shape, as what can only be described as a flying saucer, the dome shape being quite prominent. Its mobility is also quite pronounced, as it glides from side to side. Their main traction, without a doubt, is assisted by a ring of fine hairs totally surrounding their body. Beating these profusely propels them through the water. This ring of hairs is termed the ciliary girdle. Trichodina reproduce by both binary fission and conjugation. Binary fission being more common. They are able to move freely across the fish's body surfaces, attaching and detaching at will. They have a direct life cycle which can occur entirely on the host. The damaged area quickly attracts many thousand bacteria organisms, which are the parasite's intended prey. They can endure a wide range of temperatures and can be a very persistent parasite to totally eradicate. Moving on to Chilodonella, these differ from Trichodina in that they feed on plankton and cellular debris which is sloughed from the fish's body, creating their own food supply. They are able to move freely both in the water and on the fish's body, and this enables them to move from host to host if necessary. To view them under a microscope, you will need approximately 200 times magnification to identify them. They can be very mobile. Being a ciliate, they use fine hairs and flagella to propel them through the water, whipping them profusely. They use the well-known flipping motion. Usually, by the time Chilodonella are detected, they are very well established, and urgent treatment is required. In favorable conditions, they reproduce very quickly using the binary fission method. Finally, Costia. The main advantage Costia can boast is their ability to reproduce very quickly. This is achieved by longitudinal fission multiplying in a lengthways dimension. Reproduction can also occur following conjugation. As seen here, in a short time, thousands can appear buzzing around with seemingly nowhere to go. Reproduction is also possible through a wide range of temperatures. Normally, a healthy host will govern the reproduction process through its own natural defense procedures. This condition allows a symbiotic arrangement, providing the parasite is kept under control, creating a live and let live situation. They are obligate parasites with a direct life cycle spent entirely on the host. If they happen to get washed off the host, they are quite capable of finding a new host to which they quickly attach. They achieve this by beating two long flagella, which they whip from side to side, propelling them through the water. Adverse conditions cause the trophozoites to encyst, sometimes on the fish and sometimes in the water. Cysts revert to trophozoites when the conditions become favorable. Those derived from cysts must seek and find a host within a short time or they will die. There are two sources of trophozoites for transmission to new hosts: those directly from host fishes and those derived from cysts.